Here I want to talk about the first important application of the mean value theorem, and it's a very subtle point that I'm sure is overlooked in most calculus courses, at least probably at the high school level, but that is the connection between the derivative and increasing and decreasing. So let me just talk a little bit about what an increasing and decreasing function means. There's actually a definition for that, which I'm sure in many high schools they don't give you because it's probably a little too technical at first, but the definition is here. So if f is a function defined on an interval, and x1 and x2 are x values on the interval, then f increases on that interval if x1 being less than x2 always means that f of x1 is less than f of x2. So if your two inputs are related in that way, x1 is less than x2, if that implies that your outputs are related in the same way, then the function is increasing. However, if x1 is less than x2 and the reverse relationship happens, then your function is decreasing. So the subtle point I want to draw your attention to is, let's just say I have this graph here, call it f of x, and I tried to draw it so that I have one stationary point that occurs at an instant here at c, and what I want to show you is that if I were to ask you where is this function increasing, so let's just say we wanted to figure that out. A lot of students think that the fact that it flattens out at c means you shouldn't include it. But if you look closely at the definition, you actually should include c on the increasing interval in both regions, from a to c and c to b. So let's restrict our attention here first to the interval a to c. Let's just say that's our interval. Now I'm just going to pick two random x values on that interval. The first one is going to be here in the middle somewhere. And the next one, I guess, is not random. I'm going to make it c. So let's make x2 c. Well, we can see that x1 is less than x2. And is it true, or does that imply that f of x1 is less than f of x2? Well, this would be f of x1, and this would be f of x2. So, is it true that f of x1 is less than f of x2? That is true. So that means that this point c belongs on our increasing interval. So I'm going to put a hard bracket there. I'm going to say this is, and again, the point is you pick any two x values on that interval a to c, and if that relationship works, then it's increasing on that interval, and you'd need to include those x values. So you could say, okay, well, it's increasing from a to c, including the a and the c. All right, so again, I could have put x1 right below. I could have put x1 below the a, and since it satisfies the condition, we need to include the a and the c. On the other hand, let's go to the right half of this. Let's say our new I is from a to b. What makes some students uncomfortable is, how can c be included in both the a to c interval and the c to b interval? Well, the reason is because, let's say on that interval, my c is my x1, and then I pick an x2 just like anywhere over here. Now f of x1 is here, and f of x2 is here, and we can see that x1 is less than x2, and that means that f of x2 is bigger than f of x1, so that means we need to include c on this interval as well. So I'm going to say also, on the interval c to b, this function is increasing. So c gets included in both regions only because it satisfies the definition of increasing on both of those intervals. So most of the time you won't do this. You won't break it up like that. You could just say, I mean, this isn't wrong, but you can just go right through that. You could just go right through c. You can go right through c and write that it's increasing on the interval a to b. All right, so that's a subtle point about increasing, and I think it's a hard thing for students to wrap their head around, but the point is, even if you had a graph that was kind of stepwise, if you had a graph that was doing this, had all these series of steps, you could still say that it was increasing on a to b. You wouldn't have to acknowledge those flattening out points, because those are all included on those intervals that for the definition of increasing. And the same argument could be made for a decreasing. So that's a subtle point. The mean value theorem lets us use the derivative to actually talk about increasing and decreasing. So that should be intuitive, and that's great if it is. But technically speaking, there is a analytic reason for that, which I'll show you in the next video. But if we just take a look at x squared, for instance, we can see that in this red area, it's increasing, and also that the derivative is positive. Right? So let's find the derivative. Y prime is 2x, and we can see that 2x is bigger than 0 on the interval 0 to infinity. Right? Give me any x value on 0 to infinity, and you're going to get a positive value. So y prime is positive. Here y prime is negative, from negative infinity to 0, because it gives you 2x, and 2x is less than 0 on negative infinity to 0. So therefore, if I asked you where is x squared increasing and decreasing, you would say it's increasing 0 to infinity, and we're going to include the 0 because it satisfies the definition above of increasing, and it's going to be decreasing on negative infinity to 0, including the 0 as well. So 0 counts. It satisfies both definitions of increasing and decreasing. And really the only time something like that wouldn't happen, you wouldn't put a hard bracket, is if your function is it has a vertical asymptote or something funny there. But in any case, you include 0 on those intervals. So the derivative is going to tell us information about increasing and decreasing, which I think most students sort of take for granted. But technically, there is something to talk about there. Another key point, which I'll emphasize in the next video, is that the derivative, you find the derivative at a point. So to say a function is increasing at a point is technically wrong. Functions increase or decrease over intervals, which is why 0 can be included in both of these intervals. However, f prime of 0 in this case is 0. All right, so increasing and decreasing happens over intervals, and you take the derivative. That tells you about a specific point on the graph. So a lot of subtle things to talk about rather. I just want to draw your attention to that. In the next video, I'll do a proof as to why the derivative can tell us about increasing and decreasing.